In this module, we will talk about the nature of light and how it propagates. Light or visible light is an electromagnetic wave. Shown here in the figure are different wavelengths with some of its applications. We see that on the left are wavelengths that are greater than 740 nanometers. The applications for these waves are in microwaves and radio signals. On the right side of the spectrum are wavelengths that are very short, and examples of their applications are in X-rays and gamma rays that can be used for medical treatment. The visible light is the one in between. These are the wavelengths that a human eye can perceive. On the left side, the red color has a wavelength of 740 to 625 nanometer. To the right we have the violet color, which is from 435 to 380 nanometer. Light is known to have this wave-particle duality characteristics. Here we have a double-slit experiment where a light is emitted from a photon laser source and hits a double slit. The individual slits produces waves, and when these waves intersect they create an interference pattern showing the nodes and antinodes of the superposition of waves. Thus light is considered as a wave. As a particle, when light hits a surface that has an abundance of electrons that are far from the nucleus or are loosely bound, they are ejected from the surface as photoelectrons. Thus they are considered as particles since they are able to collide with the surface electrons. Light from the sun is a form of energy, and this energy is the source for all life on Earth in the form of light and heat. The sun produces light by a nuclear reaction called fusion. As atoms of hydrogen combine to form helium, they produce vast amounts of heat and light. This is how the sun produces light. Light-emitting diodes are widely used as light sources for homes. According to Statista.com, in 2030 the rough estimate of people using light-emitting diodes or LED will be about 80%. LED bulbs are vastly used in households due to its superior technology in terms of low heat production and lifetime. LED produces light by passing an electric current through a semiconducting material called a diode, which photons are emitted by the principle of electroluminescence. In the figure here we have a typical LED. Here the LED chip refers to the diode, where at the bottom shows a simplified graphical explanation on how it is able to produce light. So when current is supplied through its cathode and anode wire, the electrons recombine with the protons at the boundary of the different semiconductors. The recombination of these particles produce light and heat. Let us look into the region called the visible light or the spectrum, where we are able to perceive without any machinery for detection. The range or the wavelength of visible light is between 480 nanometer to 740 nanometer. 740 nanometer would be on the red-colored part of the spectrum, while the 380 nanometer would be the violet-colored region. The light has a particular speed called the wave speed, or commonly called speed of light, which is about 3 times 10 to the power of 8 meter per second in vacuum. If the light source, like a lamp, is stationary, it propagates spherically. Light is an electromagnetic type of wave, which means it is a combination of an electric and magnetic wave as shown in the figure. The waves are perpendicular to each other. If we take the net for the waves, we see that when it moves it appears spiral. Here we have a graphical representation of light. As mentioned earlier, light propagates spherically, and we see on the figure on the left, a continuous shells appear as it moves outward from the red point, which would be the source. Now if drawing it as rays, where rays are represented by arrows which points also the direction of it, we see that it intersects at the source point and radiates outward. The black spherical lines would be the spherical shells. We can also redraw the rays and the black lines in a way that they are perpendicular with each other, as shown on the image on the rightmost side. The purpose of drawing them as rays will allow us to graphically calculate how the light behaves, which we will show in the following slides. Here we have a simulation of reflection behavior. Reflection only occurs when light is present that illuminates an object which will bounce towards the mirror, forming an image. Here we have a mirror and an object in an upright position and lying on an axis called the optical axis. As light hits the object or the pencil, it forms rays that will strike the surface of the mirror. The arrows represents the direction of light, and as you can see, an image is formed on the right side. This image is called the virtual image, which is what we call images that are formed inside the mirror. The image formed on the mirror is called the virtual image. This image is at a position that is equal in distance from the mirror as the object. Since it is a flat mirror, the length or height of the virtual image is equal to the object. Now let us examine the nature of these rays. As mentioned earlier, we use ray models to graphically show how light behaves, and for this scenario we use them to show how it behaves with flat surface mirrors. The mechanism light behaves here is simple, since the angle of incidence ray is just equally reflected back with an equal angle called the reflected ray. Let us look at the different types of rays for a flat surface. Here we represent the object as an arrow in an upright position on the left side of the mirror, which is the reflecting surface. Parallel rays are simply drawn from the object and move parallel with respect to the optical axis. The reflected rays are formed when light bounces back from the surface of the reflecting mirror with an equal angle. An imaginary dashed line on the right side of the mirror is formed, and it is also parallel to the optical axis. Dashed lines are used to indicate that it is in a virtual space. The next ray is the central ray. The central ray is drawn from the object and intersects the vertex of the mirror. The intersection here is the intersection of the mirror, optical axis, and central ray. Since it is a flat-surfaced mirror, the angle of the reflected ray is equal to the angle of incidence according to the law of reflection. A dashed line is drawn on the right side of the mirror, and this is an extension of the reflected ray but in virtual space. To determine the position of the virtual image, we consider the intersection of the rays. Since on the left side or the real space, the parallel and central ray would never intersect on this side. So we examine the extensions on the virtual space, which is represented by the dashed line. We see that the dashed lines intersect at point indicated by the green circle. The intersection of the rays indicates the position of the virtual image. Let us look at the sign convention for the rays. The first one, the object distance s, is positive if the object is on the same side of the reflecting or refracting surface as the incoming light and the object is called a real object, otherwise, it is negative or virtual object. For the case here, the distance s of the object from the mirror line is positive since it is on the same side as the incoming light or the parallel and central rays and the reflecting surface of the mirror. And the object is considered as a real object. Now considering the distance of the virtual image from the mirror line, or s'. The image distance s' is positive if the image is on the same as the reflecting or refracting the surface as the outgoing light, and we call the image a real image, otherwise it is negative and the image is called a virtual image. For the case shown here, the distance s' is negative since it is on the opposite side with the reflecting surface. The image formed here is called the virtual image. Here we have the equations that mathematically describe the relationship of the distances and heights. As shown earlier, the distance s and s' are equal in magnitude and opposite in direction. The relation of the height is given by the magnification in equation 3. We see that the ratio of the height and ratio of the distances are equal to 1, which suggests that the height is also of equal magnitude. The positive value of magnification suggests that it has the same orientation as the object, and for this case they are both in an upright position. Here we have an example on plane mirrors. An object stands in front of a plane mirror at a distance of 10 feet from a mirror. For letter A, we are asked to find the distance between the object and the image formed. For letter B, we are asked to determine the type of image formed. We draw the problem as shown here and see that the S is equal to 10 feet. For letter A, the distance between the object and the image formed, we use the equation 2. The total distance is simply double that of either the distance S or S prime. So we see that the total distance between the object and image is 20 feet. For letter B, the type of image is determined by the sign convention. We see that the intersection of the image is positioned on the opposite side of the outgoing light and it is therefore a virtual image. Here we simulate how light behaves with objects having surfaces that are transparent. We have two types of materials here and a laser is placed in one of these material, and for this case it is in a material that is air. The laser is pointed to the surface of another material which is water. As you can see, it produces two streams of light. The one that is on the same material as the laser is called the reflected ray, and we know that it bends at an equal angle as the angle of incidence. The other ray is on the second material which is water. And you can see it bends at an angle that is slightly deviated. This refracted ray becomes more apparent when we replace water with a material glass. The physical quantity that differentiates among these materials is its index of refraction, which is given by equation 2. Where c is the speed of light and v is the speed of light in the medium. The relationship between the incident and the refracted light is given by the law of refraction or Snell's law. Here we see that the ratio of the sine of the angles of the incident and angle of refracted is equal to the inverse ratio of its index of refraction. Here we have a sample on refractive surfaces. A laser is pointed on the surface of a plane glass with an index of refraction of 1.51. Determine mathematically the angle of refraction if its angle of incidence is 60 degrees with respect to the normal line. Determine the speed of light inside the glass. Refer to the figure on the right for more details. To determine the angle of refraction mathematically, recall Snell's law as shown by equation 5. We rewrite the equation to solve for angle that is refracted, which is represented by the theta glass. Substituting the known values such as the index of refraction for air, we see that the angle refracted is about 35 degrees. Do not forget to set your calculator to degree mode. To determine the speed of light inside the glass with an index of refraction of 1.51, we use equation 4. Rewriting this and substituting the known values such as the speed of light, we see that the speed of light inside this glass is about 1.98 times 10 to the power of 8. The speed of light has slowed down inside this medium. Let us look at what rays we can use to graphically show the image. In this scenario, the object is in a material that has an index of refraction Na which is greater than Nb. The first ray that we consider is the parallel ray as shown in the image. As mentioned earlier, it is drawn parallel with respect to the optical axis and it emerges to the next media without any deviation. This is because it hits the interface at a straight line. The next ray is the central ray. As mentioned earlier, it is drawn to the vertex V. It is refracted, forming angles that is calculated using Snell's law. To graphically show the position of the image generated, we consider the point of intersection. Clearly on the outgoing rays they do not intersect at any point. However, looking at the media where incoming light is positioned, the rays intersect and show the position of the image. To calculate mathematically the relation of the images we need to know its sign conventions. For the object distance s, it is positive since it is on the same side as the outgoing light and the object is considered as a real object. For the image distance s', we see it is on the opposite side as the outgoing light, so it is negative. The image formed is considered a virtual image since it is also on the opposite side with respect to the outgoing light. To determine the relationship of the distances and height we use equation 6 where the sum of the ratio of the index of refraction and distances is equal to 0. The magnification of a plane mirror is expected to be 1, so we can say that the ratio of the height and length is equal to 1. Here we have an example on refraction of light through a plane glass. What should be the angle of incidence for a glass having an index of refraction of 1.6 with an angle of theta over 2? See figure for reference. To solve for the incident angle theta A, we use Snell's law and rewrite it to solve for theta A. This is shown in equation A. We will have to use some identities we learned in mathematics shown in equation B and C. So, we square both sides of equation A and substitute equation B and we get equation D. We then simplify equation D and substitute equation C on the left term and get equation E. We can expand the left term of equation E and we see that we can cancel similar terms on both sides. We get that the incident angle theta is equal to 73.7 degrees, which should be the angle to get this kind of refracted angle. It is also important to set your calculator to degree mode so that you will be able to arrive at this answer in degrees. Here we have a simulation of a total internal reflection. We have a material having different index of refraction. The first material where the laser is positioned is water with an index of refraction of 1.34. The second material is air-like substance with an index of refraction of 1. As you can see, the light behaves normally in the sense that when it hits the interface the light is bent as it goes to the second material. However, there is a limit to this when the light could not penetrate the second material and only produces a total internal reflection. When the laser is pointed directly downward, there is no deviation of the outgoing light. When it is tilted by some angle theta A, it deviates by some angle and we can use Snell's law to solve for the angle of deviation. When it is deviated to a theta critical, it refracts at an angle of 90 degrees with respect to the normal line and we call this total internal reflection. Total internal reflection occurs when the incident angle is equal or greater than the critical angle. Using Snell's law we can derive an expression for the critical angle. So using equation 5 we substitute the condition that the refracted angle is equal to 90 degrees. We also note that the index of ratio is less than 1, which means that the NA for the incoming light region is less than NB for the outgoing light region. So for the critical angle expression it is given by equation 8. Here we have a sample on total internal reflection. A point source of light is 0.3 meters below the water surface. What is the radius r of the largest circle at the surface through which light can emerge from the water? First we draw the problem and we see that the relationship between the radius r and the critical angle is that it forms a right triangle. By parallel relations, the angle inside the right triangle is equal to the critical angle from the total internal reflection. First we define the equation for the total internal reflection for this scenario. Using equation 8, which was derived using Snell's law, we are able to find the value of the critical angle. We then determine the radius r using the Pythagorean theorem, which is that tangent of the critical angle. The tangent of the critical angle is equal to the opposite over the adjacent, which is r over 0.3 meters. Rearranging the equation, we get an expression for the radius r, and it is about 0.342 meters. So this is the largest circle at the surface through which light can emerge from the water. Dispersion is a phenomenon where visible light enters a media like glass with an index of refraction that splits the white light into its components, which is the sum of the different colors having different wavelengths. The frequency f of the wave does not change when passing through a media. But the wavelength varies for different materials. Where lambda naught is the wavelength of light in a vacuum, n is the index of refraction. So when light disperses, it would appear like several waves being separated, like the figure shown here. Here we talk about polarization of light. Recall the graphical representation of light, which is an electromagnetic wave. The magnetic wave and electric wave are perpendicular with each other and move at a speed c, or the speed of light in vacuum. Unpolarized light contains several waves with different orientation. When it passes through a polarizer, the other waves are eliminated. Polarized light waves are light waves where they vibrate in a single plane based on the polarizer's orientation. There are a couple of ways to polarize light. First, we have the polarization by transmission. Unpolarized light is filtered by a polarizer. First, we have a superposition of electric waves with an incident intensity. As it passes through its first polarizer, it filters the other E waves and retain the wave having an angle phi. The intensity is reduced by half. It then passes through a second polarizer where it filters the X component of the E waves and retains only the Y-axis component. We see that the wave is reduced to E cosine phi. The intensity is further reduced by cosine squared of the angle phi. This is by Malus' law. The second way of polarizing light is by reflection and refraction of light. Here, unpolarized light is polarized by bouncing from a surface and absorption inside the material. When the beam of light strikes an interface so that there is a 90-degree angle between the reflected and refracted beams, the reflected beam will be polarized. To determine the angle, we use Brewster's law as shown in equation 11. The light that is reflected from the surface with the Brewster's angle is entirely polarized perpendicular to the plane of incidence. The third way of polarization is by scattering of light. Here, unpolarized light hits the atoms in a medium and the atoms' electrons vibrate, producing electromagnetic wave, and radiates outward in all directions. These waves will again hit more atoms, causing a cascade of more electromagnetic waves, and these waves are partially polarized. The clouds produce polarized light by scattering using the sunlight as the primary source. Here we sample problems on polarization by reflection and refraction. At what angle above the horizontal is the sun if sunlight reflected from the surface of a calm body of water is completely polarized? We use the Brewster equation to solve for the angle as shown by equation 11. We then deduct it from 90 degrees and we get that the angle is 36.94 degrees. This is the angle from the surface of the water. That is it for now, and I hope you learned something new today. For questions and comments you may send them to diyeslearningstuff@gmail.com. You may review the slide on YouTube at Dies Learning Stuff. Note, please do not forget to use your school email. Also write your complete name and class section. Thank you for listening and see you next module.